Hello and welcome back everyone. Today I'll be talking about something completely out of my league as a chemical engineering major. It's Broyden's method. Do you have an equation that is an absolute mess? I don't know, maybe it looks something a bit like this funny bucket, this funny horseshoe? How do I solve this? This scares and terrifies me. Well, thankfully we've got this thing called Broyden's method. We'll start basic though. We'll start with, let's say we've got some x, and x can be represented with some collection of x's, x1, x2, x others I can't be bothered to write because I don't have a tablet and I'm not writing all this out by mouse. And then we've got some function evaluated at x, which is equal to a first function at x1 and x2 and etc., and a second function and x1, x2, and etc., and enough functions that will have an n by n system. And let's also go ahead and provide a Jacobian. What is a Jacobian matrix? It's a gradient, essentially, where you've got your partial derivatives of each function, each variable to each other in a nice n by n matrix, and then this n by 1 matrix that is, a slightly. This could also be represented actually, I believe, as x. No, it could not. An adjusted x1 minus an x1, that adjusted x1 being kind of the predicted next value of about where we think we should land, based upon where we are, the current slope, all of that stuff, standard solving for equations. You multiply them together, it's still an n by n matrix, and there's Jacobian. We will need that in a bit. You don't need to memorize exactly what that is, but we'll be using it a lot. You just need to know, for the most part, it's a matrix with those partial derivatives and some differences of x. So, first, we'll define kind of what we mean by a few terms. So, we'll have a Jn. What is Jn? Well, we know it's a Jacobian, and we'll say it's equal to x of n minus the previous n, or alternatively, kind of a bit further back n. So, the previous value of x, in this case, if it's x2, it's going to be x1, or, if you've got, like a slightly adjusted x1, it's going to be the previous x1, and so on and so forth. We'll just say it's xn minus 1. So, j2, x2, x1, and we wouldn't say that j of n, that's a horrible j, that's a cool j, there we go, is about, approximately, it's going to be an f of x minus n minus f of x n minus 1. Very cool, but that was a pain to write. So let's get some newer terminologies. Let's say that's actually proportional to f of n, which is equal to f evaluated at x of n, and then, of course, minus f n minus 1, because that's about what they're going to be equal to. So that's all. I do want that, actually. That might be handy. But let's carry on and then say also that what we mean by delta x of n, because delta x will pop up a lot, is of course going to be x of n minus x of n minus 1. It's a very droopy x. It's not having the best day. Please, everyone, comfort this x. It needs some love. So with that, we know that j of n, a bit of a math here going on, and then delta x of n is somewhere around equal to f of n, the change there. That's pretty important. We'll need that for later. And then we'll get to some methods. So how would you go about solving an equation in the first place if you're trying to, figure out where this equation is going to be when it's going to be 0? Well, you've got a couple methods. You've got your classic secant. You got your f prime of xn. It's going to be more or less equal to f of n, f n minus 1, all that over delta xn. That's like your pre-calc stuff. It's good for guesstimation, but the truth is, it sucks. Right? That's objective math. You cannot disagree with me on that. It's impossible. It sucks. For really very precise calculations. For a first guess, it's pretty solid, very lightweight, It's lightweight for a reason. Cool. So we've just got this dude, Newton. He's famous for dying a virgin and also something about like apples and stuff. I don't know. That seems like a bunch of nerd garbage. What we do need to know is he maybe invented calculus. Might have been Leibniz. I think. It's very contested. We're not, however, here to aggravate the math fandom. We're here to say that x plus, or perhaps x of n plus 1, your next value in your iterative series, it's going to be, you know, x of n minus, well, say, the function evaluated at n over the function n prime. Cool, that's better. That's way better than whatever we were doing for secant method. Here's the thing, though. It still sucks. Let me make sure we all get that. Sucks. Less, but still sucks. We'll double underline it so we know which one sucks more. In terms of very precise calculation, this one's better. Great for moderate weight calculations. But let's say, again, my function is this funny bucket. This funny horseshoe. It scares and terrifies me, and I cannot sleep at night when Rosenbrock here has invaded my dreams with his weird bucket horseshoe function. I need something more powerful to banish these mathematical demons. Well, we're going to whip out this dude. His name is Broyden. At least his method. I don't know where he is nowadays, so I'm not sure if I can summon him instantly. But we can summon his math. With a bit of Jn, that's a Jacobian. Is going to be our previous iteration of the Jacobian, plus, and hang with me, this is going to be a bit of a pain to write. I'll try and do it slowly, so it's not illegible, as I already make it illegible. We'll say we've got a good, nice, solid, the change in the value of function evaluated at n, minus, say, perhaps, j, the previous value, and then multiplied by the change in x, all over a very funky thing that basically it's just the square root of the sum of the squares. It's a way of writing it so it's not, you know, I don't have to write square root of x1 squared plus x2 squared plus x3 squared, because that's a pain, and I don't have time for that, and I don't want to do that. So we're just going to do x n squared. That's what that means. It's a square normal. And then let's go ahead and, for good measure, add on an x of n and transpose it. As you might remember, that is actually a vector. We've got a whole line of them. So let's flip them sideways so we can get a nice box of them. We might want a box, say, because the Jacobian's also a box. So now everything is kind of all boxed up. Very nice. What does any of this mean, and how did we get there? Well, you saw the Jacobian, and what you need to know is that the function a bit further forward, so, you know, we've got a point here, here's x of n, here's f of n, and we're going to say the function goes this way. That's not how you drag. That's not how you drag. How do I drag this? This is very inconvenient. I'll try not to write off the screen. X of n, but a bit further, so we're a little more iterated. And then f of n, but a bit more iterated. So there's our fn iterated. It's somewhere over there. It's a bit closer to the actual value, which is nice. We like being close to the actual value. That's how we solve things. So we've got our f plus, and that, based upon a couple other things, is going to be equal to, we'll say f1 is equal to f1 plus some stuff I really don't want to write because it's a bit of a mess. But the shorthand of it is delta f1 over del x1, the partial derivative of each function of the function to each x value, there'll be a del xn here, and then it's going to be, that's a 1 by n, here's an n by 1, that is basically a stack of xn plus minus xn. Now that should look awfully familiar, like perhaps we've got it there, the x2 plus minus x2. Well, that's just extrapolated out to our nth size matrix. So you stack them up. We'll notice it's a bit Jacobian looking, and with that, we do in fact have a thing where j x plus minus x is equal to negative f. That should also look quite familiar. That was there. They're about the same, pretty much. And finally, we can actually, with this f1, we also should know then that x. No, that's not an x. I've written two things and I thought a third. F plus is going to be about the function of f plus the Jacobian x plus minus x. That's kind of looking a lot like Newton's method here. Don't forget, it still sucks. Only works for like a small bit of stuff. Decent, mid-weight. We could do better. We are doing better. In other words, we've got, say, a variable. We've got, we've got our x's. We've got our iteratives. We've got that. So if we combine this all down, what we'll have here is that our function f plus is going to be more or less equal, enough that we're not super concerned about it, f plus a slightly modified Jacobian plus x. Because yes, we could do without the modified Jacobian, but the truth is, then we've got one Jacobian, and we're kind of hoping the Jacobian at no point needs to change. That's fair for some equations, but we can do better. We can have a Jacobian that updates based upon our now improved knowledge of where the function should be going, so it's a bit stronger. Cool, what's this updated Jacobian? That scares me. Well, what you need to know is that it really should be 0, should be more or less. It shouldn't be going anywhere. J delta x, I believe, and then f plus should be equal to j plus minus j over the change in j delta x. And that looks a bit secanty, doesn't it? Don't forget, still sucks. We can do better. So from there, what is this j plus still? We're getting closer. We've got to use somewhere, but I don't know, man. Well, here's where we can introduce a third chunk into our equation. Don't think too hard about it, because it's gonna scare you a bit. We're going to introduce a second perpendicular value. Arbitrary, doesn't matter, cancels out. This is where I get super lost, but it works. That's what we all need to know. We're going to call it y, because why are we doing this? That's what it's short for. So, we've got here's the one constraint of y we need to know. J plus y is equal to jy. That's why it's perpendicular. As I tried to point at the screen, if that would help, I'll point at this instead. As x and f change to f and x iterated, a bit closer, y should always be going perpendicular to the movement, and should always be calculated so that it always makes sure that the Jacobian actually, there's an equivalence there. This should scare a lot of math people, potentially, because I've just said that the j and j plus might be the same thing, but, this is fun math, where things just work if, this is why it actually works, y is that's not very good, perpendicular to delta x. That's also very important. So, let's establish some things here. Delta j, or perhaps iterate on some things. Delta j, delta x is equal to f plus. As we established, kind of around there, a bit down there, and that's what it is. What we do know is that delta j y is equal to 0, as we just said. And our x's dot our y's should also be 0 because they're perpendicular. Let's make sure that's a 0 and not a 6. We don't want any 6's hanging out in our math. And with that, we know two things. Two very important states this thing should be in. Delta jy is equal to, I can do a better curly bracket. There we go. F plus for y is equal to the change in y is equal to the change in x, and 0 at y dot del x. I've made a mistake. Hold on. That's not delta. Now this math makes sense. Equal to 0. 0 that does not look like an errant pair. There. That's some good tasty math. So we know two things about it, and we can solve from there. So we're gonna have some funny math. Let's say delta jy is going to be equal to, because I'm seeing a y hanging out here. If we can get these y's to be on each side of the equation, it doesn't matter what y is. It'll be truly arbitrary. Wouldn't that be nice? Well, good news. We'll say y dot delta x over delta x dot delta x, kind of our two states of being, because y is delta x, so that should be the same. And then we'll add in an f plus, kind of other state of being. And, well, that can be cleaned up a bit. We'll say delta x transpose. Effectively meaning we flipped it around 90 degrees, so we're kind of already dot producting it initially. And now it's not direction sensitive. So always end up about the same way, because it has to be written that way around, so that y is now tagging on second. And we'll say it's delta x absolute value squared. That's like an awfully familiar term to some degree. Jeez. It's supposed to be already here, but there's a lot of mucus. Very rude of it. And again, we have the f plus. Great. So, with that, you might notice a thing. If you've got a y hanging out here in a suspicious location, perhaps we could, I don't know, flip them. Well, we can. And if we flip them, say this f plus and this y, if they could somehow be switched around, if they were, say, equally sized matrices, which, well, they should be. Because remember, it does in fact dot product quite well off of x. So, there's very likely a whole, since f is going the same shape as x. No. Square. Fun matrix things happen that I'm entirely sure about. I'm not a math major. If you think I'm doing something wrong, you can scream at me by means of comments, or maybe Twitter, or pigeon mail, or just yelling into the wind and hoping an errant gust carries your complaints to me. Anyway works. We can just go ahead and condense some terms out and say that delta j is going to be equal to an updated function value, a bit closer to where it should be, the transpose of delta x, and a delta x squared. I like this one. It's very good. We can do something with this. In fact, this should look a bit familiar to kind of like that. Because I'm seeing here, there's definitely a j, a delta j, which we've got. We've got here our xn, or an xn transpose. We've got this funny square term. So you have to get some of these extra j terms in there somehow. Well, conveniently, there is, thanks to a little bit of thing we're going to call, which we're not calling, it's already called, the Sherman-Morrison method, which is, let's say we've got a plus u v transpose, so it's a nice square, and with the inverse of that. Well, that seems like a hot mess to get, and I don't like that, but we've got a bit of a transpose there, I suppose. Now, how do we go about transposing all this to get, this mess? Well, who knows? Thanks to Sherman-Morrison method here, we'll say that should be equal to just the inverse of a bit easier to calculate, minus, get used to seeing the inverse of a, and u v transpose, a inverse again. I'm not entirely sure I need two of them, but I suppose we do. Sherman and Morrison did better than I did. And then a bit of a 1 plus v transpose a inverse u. I wish I could shortcut without erasing it, but I suppose I can redraw the line, and that is, I'll write it a bit nicer for you. Sherman Morrison. We can do better. We can do better. There. Now that's legible, mostly. That's Sherman-Morrison. A great way of, of making a very messy function. This is messy, the inverse isn't pretty, and we can do better. It's something a bit cleaner. And in fact, this one's even worse. Computers hate this. Do this one thing and computers will hate you. It's called a lot of matrix calculations. They require a lot of variables. So, but by combining this previous method that we established up here with a bit of Sherman-Morrison magic on that delta J term, we can establish some important things, namely that the Jacobian inverse is going to equal to Jacobian inverse at the previous value. Check my nice paper note here to make sure I'm not going crazy. Checking. Yeah, that should be about right. Because from there, plus 1. Oh, that gets very messy. Changing xn minus jn minus 1 inverse delta f of n over delta x and transpose that boy again. More of the same. We really love these transposes. And just another one of these for good measure. Alright, that's messy. I don't like looking at that. Let's just get this down so we can finally get what we're really aiming for, if I didn't already write it up here, which I didn't. Good. Cool. How does this relate to function? That's what we're here for, right? We're not solving Jacobians, we're solving functions. Well, this is where the magic happens. F plus, that thing we wanted, a bit better version of x, a little closer to where the actual solution is going to be the function at its current value plus the Jacobian plus the function iterated a bit. Don't ask how it gets back in there, but it does. A delta x transpose all over that nice term we might remember. This one, the squared normal, and then a nice x delta x, which is then itself equal to the function plus j plus, or j a bit further, delta x. Now, this one has, a little ahead of myself here, a constraint of j plus minus j. I suppose that's meaning to be a squared. Don't go running off. This here. This is what we were all trying to solve for. There's how we get a bit better function. And eventually, that will take us to somewhere nice. I suppose I explained something a bit up here in Sherman-Morrison, and what all these u's and v's actually translate down to. As it turns out, it is j plus equals j plus uv. As you might remember, we had that a plus uv transpose. Here we have j plus uv transpose, very similar sounding, where u is equal to f plus, and v is equal to delta x transpose over squared normal delta x squared, or just squared normal delta x. With these two things, they plug back in to this equation, because that's how that then becomes, that f plus is two things, because that delta j is really just a fun way of writing j plus minus j, which then of course means j plus is going to be equal to j minus f plus delta x transpose delta x normal squared, and that translates into those things. And that transpose and inverse is actually not that hard for the machine to do, so they go into this equation, so that translates down here into this bigger equation, and that'll simplify down eventually into this nice, pretty solution for getting our equation out of our Jacobian. If at any point you're lost, welcome to the club. I only managed to stumble on down here and figure some things out last second. I'm glad I took good notes in class. Hopefully, you learned something, like the Broyden method. Let me spell that for you. I actually spelled it wrong a few times. Broyden method. And that's going to let us tell Newton what for, tell Mr. Secant what for, tell Mr. Sherman-Morrison he's pretty cool, because this is what we were really here for. This will let us solve some messy set of equations that's got a whole bunch of x's and a bunch of functions, and then maybe Jacobian for good measure, maybe some gradients. Let us solve it. Like, I don't know, say, this terrifying function. Coming for you, Rosenbrock. Your function will be no match for my Broyden method. We'll get to that next part.